Okay. We're going to expand on our idea of trigonometric ratios today to create trigonometric functions. Now, the idea is, or the question probably right away says, well, what's the difference? To be honest, not much. But let's go back and think of functions and what they do. A function in general takes an input and gives an output. So when we look at a graph, what we're seeing is a visual representation of how the output changes based on the input. We align our inputs from left to right on the x-axis, our outputs bottom to top, y-axis, and we can see how those y values change as those x values change, and that's what we call a graph, and that's how a graph is useful. So when we think of trig as a function, what we're doing is we're assigning this idea that if we take an input and then apply a trig function to it, whatever we get back would be considered the output. Well, let's think about what that means in terms of trigonometry. Well, when we have sine of x equals y, we'll go to our xy notation, which we're used to as input and output. The question is, well, what is this input? And then it will generate some sort of output. Well, what goes into a sine function, for example, or a cosine or tangent or cosecant or anything else? But for any trig function, what goes in and then what comes out? Well, the answer is our input is an angle measure. The way we initially described it was the acute angle of a right triangle. We expanded that using reference angles to include any angle, because we can always create a right triangle using the reference angle from it. So regardless, an angle goes in, and what comes out is a ratio. And we gave those ratios different names. So for this example, I used the sine function, and an input of an angle gave a ratio, specifically the sine ratio. So let's look at an example with a number here. Hopefully we don't have to use our unit circle to evaluate this, but let's take a look. So let's say we want the sine of pi over 3. Well, let's look at what we just did. We took a function, sine, we put into it pi over 3, and the output will be a specific ratio, in this case the sine ratio. So what is the sine ratio of pi over 3? Well, the sine of pi over 3 is simply, nope, it's the square root of 3 over 2. Okay, so what we actually have here is an input and output pairing with the sine function, which is where we're trying to go today. So today we're going to look at creating the graphs of sine and cosine. So far we know that the graph of sine of x, or the graph of y equals sine of x, will have the coordinate pi over 3 square root of 3 over 2 on it, because that's an input and output pairing. Input is an angle, output is a ratio. Okay, now let's go through and create our first trigonometric functions, or the graph of our first trigonometric function. So let's create the graph y equals the sine of x. And as usual, or as always, we will revert back to our original input-output pairings. We're going to do it a little differently here. We're actually going to focus on the values of the unit circle as we work our way around. So, first and foremost, the unit circle gives us the values for any number of rotations, any direction. We're going to focus from 0 to 2 pi. So we're going to create our graph just from 0 to 2 pi first, and then we'll talk about how we can use that to create the rest of the coordinate plane, or the rest of the graph of y equals sine of x. So, using the unit circle, let's start and just identify what the sine values are of this on the unit circle as we work our way around. So pi over 6, sine is 1/2. Then we have root 2 over 2, then we have root 3 over 2, then we have 1, we have root 3 over 2, we have root 2 over 2, we have 1/2, we have 0, we have negative 1/2, negative root 2 over 2, negative root 3 over 2, we have negative 1, we have negative root 3 over 2, we have negative root 2 over 2, and we have negative 1/2. So what we have here is a hodgepodge of values, but let's think about what we actually are looking at. These are all the outputs based on the different angles. And we know the angles, we know the outputs, but I can kind of see them here, which is nice. Now, let's talk about what we actually are capable of graphing here, because some of these are pretty difficult for us to actually put on a graph. So we're going to have to just kind of figure out an approximation to graph, to base our graph on. So all these values are essentially very few numbers. Positives and negatives of essentially the same thing. So sine value starts at 0 and 1. I'm pretty good at graphing that. There seems to be sine values of 1/2. I know that is. Root 2 over 2, I don't know where that is. Root 3 over 2, I'm not that quite sure. So let me just get some approximations here. Root 2 divided by 2 is about 0.7, and root 3 divided by 2 is about 0.85. Okay, so that gives me an idea of where to put them, just to create the shape, and then most of the time what we'll find is we don't really need those points to create a nice sketch of y equals sine of x. So looking here, we can see that the minimum output is -1, and the maximum output is 1. Remember, this is the unit circle, 1 unit radius. Sine is the y value of this. So we're looking at how high and how low does this go as our angle travels around, because our angle is our input. So this angle is rotating around. That's going to be along our x-axis, and the output is this y value. We kind of see that it's going to oscillate, which will end up being one of the key pieces to this puzzle. So my maximum is 1, minimum is -1. And just like this rotation by the coordinate plane is broken into 4 sections, let's break our graph into 4 sections. So right now I have one rotation around our circle, 0 to 2 pi kind of laid out here. I put pi down. Now I'm going to put pi over 2 just so I can see those quarter marks. And then I have 3 pi over 2. So these will create our 0 to 2 pi, one full rotation split into quarters. And that's going to become a common theme as we work through these pieces. Okay, so let's plot the points that we're most familiar with. So at angle 0, the sine value is 0. So I have a point here. At angle pi over 2, the sine value is 1. At angle pi, the sine value is 0 again. At angle 3 pi over 2, the sine value is -1. And at angle 2 pi, we're back to 0. So we can get a decent look at what it's doing. We know the graph has to hit these points. Let's go ahead and throw our approximations in for the rest. So pi over 4 would be here, which is root 2 over 2, which is about 0.7. So that's about here, just estimating there. Pi over 6 is approximately maybe here. Pi over 6 is 1/2. Pi over 3 should be right about here as far as the angle, and it gives me root 3 over 2, which is about 0.8. So that gives me a pretty good look at what this does. Continuing, I have points go in the other direction, and I have the negative versions. Well, what we find if we plot all of those is we have a nice behavior that this sine value follows, and that it's smooth. It has these curves to it. In other words, we're looking at how the y value of our rotation changes. Well, if you think about it, our y value, if we follow just what is happening to the y, or how high and low we are on our graph, we go up quickly at first and then slower until we reach a height of 1, which is a maximum. We then start decreasing slowly, increasing the speed at which we're decreasing our height until we reach 0 again, and then we repeat in the negative direction until we're back where we started. So this is our sine function. Now, I'd like to look at some key points, because we had actually 4 points that if we, or 5 points rather, if we had known that this sine function was going to follow this nice smooth curve, then we would have just been able to address it using these points here. And what we're going to end up finding is that these quarter points are going to be the key components to graphing a sine function. All right, what I would like you to do now is I would like you to graph y equals the cosine of x. Very similar idea. I'd like you to graph it from 0 to 2 pi. On this axis. Go ahead and pause the video and do so. Okay, so first off, let's look at just these key components. We're going to look at just these quarter spots. So this is the angle 0, and the cosine there is 1. This is the angle pi over 2. The cosine there is 0, the x value. This is the angle pi. Cosine there is negative 1. Cosine at 3 pi over 2, sorry about that, is 0 again. And then when we return to 2 pi, we're at the same location as 0, and we're back at 1. So what we find is that the cosine follows a very similar pattern as the sine function. So what we have now are the sine and cosine functions, each graphed from 0 to 2 pi. Now, let's go through a couple of these things. First off, what they have in common, as well as a few terms that we are going to become very dependent upon. So, using this, let's go through a few of the things that we're already quite familiar with. First off, the domain. Well, the domain is the collection of all inputs of a function. Well, in this case, our inputs, as we discussed already, are the values of angles. Well, we have two types of angles. We have positive and negative angles. Well, positive angles rotate counterclockwise, and negative angles rotate clockwise. Well, the question is, what kind of angles, or what are the limits on how many times or how far we can rotate? Well, is there any limit in how far we can rotate or how many times we can go around this circle in the positive direction? No. How about the negative direction? Again, no. So the domain of these is negative infinity to infinity. Range. Well, we can see on the graphs the highest values, the maximums are at 1, the minimums are at negative 1 on each. All the values in between are spoken for. So the range of both of these functions, are negative 1 to 1. Minimum of negative 1 and a maximum of 1. Now, we have a few other terms regarding these trig functions, sine and cosine, or a generic term for both of them would be called sinusoidal functions. The first is this measure here. How high or how much higher and lower the graph goes from a center. Well, that defines two different terms as far as these functions are concerned. The height of the peaks, or the depth of the valleys, is referred to as the amplitude. And in standard form, or the parent functions for sine and cosine functions, the amplitude is just 1. Now, what we call these horizontal lines that these graphs go above and below from, these are the axes of oscillation. In other words, those are the horizontal lines that these graphs go above and below. Originally, in their parent functions, as we have here, they go above and below 0, or y equals 0. Now, one more term we need to look at here is what's referred to as the period. The period is the horizontal distance that these graphs take along the x-axis to complete one rotation. Or we'll change it slightly based on what the graph looks like, but it's the shape that is created by one rotation, which are all we're looking at here. So what we have, the period, is simply the distance from beginning to end of one rotation. So at this point, our periods are simply 2 pi, meaning a rotation from 0 to 2 pi along our unit circle create one of these pieces. Now, we said the domain goes negative infinity to infinity, but we only see 0 to 2 pi. So the next question is, well, what would happen on both ends of each of these functions? Well, each rotation in the positive direction along this circle is repeated by the same behavior. So what we'd find is that this behavior repeats. So this is one period. It's 2 pi units wide, and that would then repeat for forever. So if we zoomed out on this and looked at our cosine function, we would find that it would continue that pattern, that wave function, over and over again throughout its domain. Now, let's look at this and apply this to a sinusoidal function, meaning a function of either of these kinds, but with all of our transformations inside of them. So, let's have a go at it. I'm going to use this sheet as my reference to create my graphs and apply what we know to these new parent functions. So what we're looking at is what's referred to as sinusoidal functions. Oh my goodness, I'm drawing a blank here. Sinusoidal? That's spelled wrong. Functions. Oh my goodness, I'm going to have to look that up. I'm sorry, that's going to bother me too much. Apparently I'm not going to find it. Okay, so sinusoidal functions are these two functions, each specific families of functions. We have y equals a times the sine of, and this is going to look familiar, I hope, b times x minus h plus k, and same transformations, same effects of the cosine of b times x minus h plus k. Now, let's discuss what these things do to our functions. So, first and foremost, a is on the outside. It's a vertical multiplier. B, multiplying on the inside, it's a horizontal multiplier. Well, keep in mind that horizontal multipliers behave in the inverse manner. So if I multiplied by 2, it would actually contract by a factor of 1/2. If I multiplied by 1/2, it would actually expand by a factor of 2. So on and so forth. It has that same effect as we discussed in our warm-up today. H is our horizontal shift, meaning we shift this left or right. Again, inverse. Adding moves to the left, subtracting moves to the right. And K is our vertical shifter. Again, moving up and down. Now, let's talk about what that actually does to these ideas. So, if we think of these functions here, we have these new terms. First and foremost, a outside multiplier, the value of our a. Well, we're taking these graphs and we would be stretching them vertically. Which of these new terms does that change? Well, what we find is a actually becomes what defines the amplitude of these functions. Now, amplitude is just a positive distance, so we find that the amplitude is always the absolute value of a. B is a horizontal multiplier, so it's going to take these functions and it's going to contract or expand them. In other words, we're going to have the effect of essentially taking a sine function, something that looks like this, and either making them contract so it happens faster, or expand so it happens slower. Regardless, what's changing when we contract or expand these functions horizontally is we're affecting the period. Well, we have a formula for that. If we have the period as the distance horizontally that our parent function originally takes up for each rotation, which is 2 pi, and we are going to contract by a factor of b or expand by a factor of b, well, we're multiplying or dividing. So what we find is the period will always be just 2 pi over whatever the b value is in these pieces. H is a horizontal shift. Well, excuse me, in sinusoidal functions, we call those phase shifts. So H is the phase shift, which is just a horizontal shift. And lastly, K is our vertical shift. Well, K, in our parent function, there is none, so it's 0, identifies the axis of oscillation. Because if we take this entire function and shift it up or down, we have to base that on an axis of oscillation. So our axis of oscillation is always y equals that k value, because the entire piece is being shifted up or down. Now, let's go back to these functions and let's identify what it is, or what are the key points that we actually need to graph in order to see what this function looks like. And let's think of it in terms of periods. So there's a period that starts at 0 and ends at 2 pi. And if we split them into 4 sections, cosine goes from 1 to 0 to negative 1 to 0 to 1, while sine goes from 0 to 1 to 0 to negative 1 to 1. So regardless of what that period is, no matter how much we stretch this out or contract this, whatever the period is, each of these behaviors will occur at the quarter marks of that period. So let's take a look at an example together. Let's graph y equals the sine of 2x as a function. First off, the parent function for sine of 2x would be sine of x. So let's graph this on the interval 0 to 2 pi. And what I'm going to do to start is I'm just going to create the sine function so that we can see how that changes by this factor of 2, or this horizontal multiply by 2. Well, let's sketch that graph on there first. To do that, I'm going to use hopefully a pencil. Let's see if it shows up. Yeah, I'm going to use a pencil, and I'm going to graph y equals sine of x. So y equals sine of x was the following. It went from 0 to 1 to 0 to negative 1 back to 0. And this we're going to call the parent function for all sine functions. Just like any other parent function, it's the function that we can apply those, looks like I need to go a little darker, that we can apply those transformations to in order to create, there we go, that's better, in order to create our entire family of functions. Now, this too is going to take our period and contract it. So the period was once 2 pi, but our new period is going to be 2 pi over b. Well, the b value here is 2. So my period is simply 2 pi over 2, which is pi. So I know that one of these patterns of the sine function, or essentially one rotation around the unit circle, instead of happening over a horizontal distance of 0 to 2 pi, it's going to happen from 0 to pi. Well, let's just over here on the side think about what behaviors must occur. So regardless of what the period is, if we split it into two parts, we know that these key points will create the same behaviors of the sine function. So we're going to take these and contract them. So instead of this 0 to 1 to 0 to negative 1 to 0 pattern of the sine function happening from 0 to 2 pi, we want it to happen from 0 to pi. So here I have now split one period into its four components. Let me transfer that here. So from 0 to 2 pi, instead of seeing one single period of the graph y equals 2x, we are actually going to see two periods of the graph y equals 2x. But it'll follow the same pattern. So my sine value starts at 0. A quarter of a period generates a maximum at 1. Half a period generates a 0. 3/4 of a period generates a minimum at negative 1. And a full period generates a 0 again. So here we see that same first period of this function. This is our new function now, though. It is sine of 2x. We can see that we took sine of x. The same thing happens, but in half the distance, because this horizontal multiplier of 2. So we do that. Now, after this occurs, the pattern repeats. So we have a maximum, a 0, a minimum, and then a 0 again, and we can repeat our pattern. And now we have this graph. Looks like I got a little wide there, but we have this graph that is repeating over the course of its period for forever. Okay. Now, let's do a quick reminder of how to apply each of these shifts. So the shift or the transformation order. When we have a sinusoidal function, we want to apply the following transformations in order. First, period change. This is the horizontal multiplier. Second, phase shift. That is the horizontal shift. That is your h value. Third, we have a vertical multiplier. That is our b value, or sorry, our a value. That creates a different amplitude. And lastly, we have a vertical shift. That is our k value, and it creates a axis of oscillation. Okay. Your turn. Please graph the following. Okay. Pause the video. Take your time. Go. Oh, I'm sorry. Don't go. We're going to graph this from 0 to 4 pi. There we go. Okay. Take your time. Go ahead and graph this. Okay. So here we have it. First and foremost, if I'm going to go from 0 to 4 pi, I need a little bit of reference as far as where we are at. So the first thing we want to determine is what is the period. Well, the period is always 2 pi over b. In this case, my b value is 1/2, so that's 2 pi divided by 1/2. Divided by the fraction is the same as multiplying by reciprocal. So divided by 1/2 is the same as multiplying by 2, so this is 4 pi. So I have my period as 4 pi. So I need to break 4 pi, or 0 to 4 pi, into quarters, because that's where my key values are going to occur. So half is 2 pi, pi, and 3 pi. So it turns out we're actually only, from 0 to 4 pi, going to be able to graph one single period of this function. So what we need to do is we now need to graph this. So I'm going to graph this. I'm going to use some colors here. I'm going to graph this one in pencil. No, I'm not. I'm going to graph it in pen. I'm going to graph this in pen. This is the cosine function. So if you think of the cosine function, looks like it's a purple pen. The cosine function starts at 1, then goes to 0, -1, and back to 0. And that's at the quarters of a rotation. Well, that translates to the quarters of a period. So the cosine function will start at 1, then go to 0, -1, 1, and then back to 0. So this is not exactly my parent function, because parent functions are defined as functions with no transformations at all. I have done just this 1/2 piece. It is a change of period for my cosine function. So this period is now, or this cosine graph, now includes just the change in period. Now, next graph, next thing I'm going to apply to this is my vertical shift, or my vertical stretch. It's a multiplier by 2, changes the amplitude. So right now this graph is going up and down 1 unit from this axis of oscillation. Well, that means all my y values are going to be doubled. This y value is 1, so it'll become 2. 0 times 2 is 0. -1 for a y value becomes -2. 0 becomes 0. 1 for a y value becomes +2. And now I have this graph. It's in green. I'm going to go ahead and put a dash mark on it, as it's not my final solution. Okay. So now what we have applied, the green graph, is the purple graph stretched by a factor of 2 vertically. So we now applied that vertical multiplier. And we're now ready for our last shift, which is that +1, that k value. And that creates a vertical shift. Well, my axis of oscillation was at y = 0, so if I shift that up, I always like to include it. This is my new axis of oscillation. So all of these zeros are going to shift up 1, so they'll now be on the axis of oscillation. My maximums will also shift up 1. So there's 2. This minimum goes from -2 to -1. This maximum goes from 2 to 3. And now I have my final graph of this function. Okay. Very well. It's your turn to give them a go. Your assignment for this lesson, page 327, 39 through 47, and 73 through 76. Okay. Please give these a go. We will continue with this task on Monday and pick up with it on Tuesday. All righty.